Okay, pre-calculus, this is the integration introduction. This is not in your notes. I just want you to get a feel for how we can use what's called integration, which is essentially finding areas and volumes by taking small pieces, slicing stuff into small pieces. We're going to do a fairly simple problem that doesn't seem like we would need calculus for, and we really don't at first, but it just is highlighting how we can use this process. So let's say that we have a car, there's Zeno's car, traveling at a constant 1 mile per minute for 10 minutes. So notice that my velocity is the y-axis, time is on the x-axis. Since his velocity never increases, I have a nice straight horizontal line for 10 minutes. He just goes at a constant rate. We're going to use our old dirt equation though here. Distance equals rate times time. So the velocity really we can think of as the rate. Well, since rate times time is velocity, rate times time is distance, I can find the area underneath this blue line. So looking at this rectangle down here, if I find the area of it, base times height, well, the base is time, the height is the rate, so the area of this rectangle, rate times time, gives me the distance. This is a weird way to think of it, but really, the distance the car traveled is equal to the area of that rectangle. So, how far did it go? Well, this one's pretty easy. 10 by 1, so it went 10 miles. Which obviously, if it was going 1 mile per minute for 10 minutes, it went 10 miles. Obviously, that's a fairly simple example, but it illustrates how we can use areas to find stuff that you usually wouldn't think as an area. Well, now let's take a little more interesting example. Now assume that the car is somehow able to instantly increase its speed by 1 mile per minute every 2 minutes. So from minute 0 to 2, it's going 1 mile per minute. And then magically it can just instantly increase, and for 2 minutes go 2 miles per minute, and then instantly increase 3 miles per minute, 4 miles per minute, 5 miles per minute. Now we're obviously getting somewhat out of the range of reality here if we're going 5 miles per minute, but let's just go with it. Assume this is a really fast car. Again, Zeno has a massive engine in that thing. So how far did the car travel? Well, I don't just have a single rectangle, but if I find the area underneath all of these little blue line segments, basically it's a bunch of individual rectangles. Again, each rectangle has a base, that's the time, and a height, that's the rate. So the area of the rectangle is the rate times the time, which is, therefore, the area is the distance. So, if we just find the area of each one of these, this is 2 by 1, so that's 2. The next one's going to be 2 by 2, so 4, 2 by 3, 6, 2 by 4, 8, 2 by 5, 10. So if I add up all of those individual areas, I have the total distance that the car traveled. Because again, the area of each of those rectangles represents the distance traveled over that time. And all those add up to equal 30. And again, that is the distance. So 30 miles. Okay, now this problem, besides the fact that Zeno's car's going fast, it's also not really a very realistic option here because, again, it's instantly increasing, instantly increasing, instantly increasing, which we can't do. So now we're going to look at Zeno's car accelerating the whole time. So the velocity, notice now I don't have horizontal segments. The velocity is increasing because he's accelerating. So slowly accelerating. Again, if we want to know how far he's traveled, we can find the area underneath this graph. That will represent how far he's traveled. Now, yes, I understand this is a right triangle, but let's assume that we have no idea how to find the area of a right triangle. We only can do rectangles. We're not smart enough to figure out the triangle thing yet. Well, again, we can't just simply use the rectangles like before. So what we're going to do, we're going to compare Zeno's blue car to some other green car. I don't know, maybe Newton's driving this car or something. So what we're going to do is say that the green car starts trailing. So he's going 0 miles per minute for the first 2 minutes. So the green car for 2 minutes isn't actually going anywhere. The velocity is 0. And then this green car instantly jumps, just like the blue car did before. And then instantly jumps. Instantly jumps, instantly jumps. Its velocity instantly jumps every 2 minutes. Well, if we find the area underneath the green, and really there is no rectangle here, then we have an estimation of the area underneath the blue. So this would be 2 times 2, 2 times 4, 2 times 6, 2 times 8. So if I add up all of those, that tells me how far this mysterious green car that doesn't really exist or can't possibly do this, but instantly accelerates, how far it went. Which if you add those up, you get 40 miles. Now again, why am I using that green car? I'm using that to estimate the distance that Zeno's blue car went. Now, looking at this estimation, it's obviously short of what it should be because we have all this excess area that we did not account for. Well, we can remedy that by now looking at the green car, but now the green car is going to be beating Zeno the whole time. It's going to start off this race already moving at 2 miles per minute for 2 minutes. And then it's going to jump to 4 miles per minute. Then it's going to jump to 6, then to 8, then to 10. So now the green car is always ahead of Zeno. The second Zeno's car catches up, the green car, boom, accelerates instantly. Which obviously, again, cannot happen. But we're going with it. Now, if I find the area of all these rectangles, 2 times 2, 2 times 4, 2 times 6, 2 times 8, and 2 times 10. Now I have another estimation of the area underneath the blue. And so if I add up all of those, I get an area of 60, which means that the green car went a total of 60 miles. Now, compared to the previous problem, this one now is an overestimation because I calculated all this extra area that's not actually underneath that blue line. So what we can do then is take that underestimation of 40 miles from the previous page and this overestimation of 60 miles from this page and find the average. So if we average out the over and the underestimation, we get that Zeno's car must have gone 50 miles total, which now suddenly magically we figure out that yes, we can find the area of a right triangle. Suddenly the theorem was bestowed upon us from Euclid. So magically we can find the area of that triangle, which represents the distance Zeno went, and it's a 10 by 10 triangle, so 1/2 base times height gives us, go figure, 50. Now this problem was an oversimplified problem in that the underestimation and the overestimations averaged out to be the right answer. That's not always true, but at least it gives you something close. Now, had we used more rectangles, what we would have got is a more precise answer. So this shows, had we used more rectangles, each rectangle with a base of 1 instead, all the way across, we would have got a better estimation. And again, as we use more and more rectangles, we get better and better estimation. So here's another animation of that happening. To find the area under that curve, more rectangles I use, the closer I get to the actual area. Again, it's never quite perfect, but I've got these little areas over and these little areas under on the other side. So overall, I get a pretty good estimation of the area.